Welcome to the video Directional Derivatives and Linear Approximations. In this video, we will discuss the directional derivative of f at a point P in a direction given by u hat, and we'll explain and see examples of this type of formula. And we also want to look at linear approximations, which are given by this type of formula. So we will see where this comes from later in this video. For these two things, we could have, for this first one, we could have a picture like what we have over here. Here is the xy plane, the x-axis being horizontal, the y-axis being vertical. We have a point P, which for instance could be the point with rectangular coordinates 1, 2, and we have a vector of length 1. A unit vector pointing in some direction. These are the things we need in addition to knowing the formula for the function f of xy in this case, so that we can evaluate directional derivatives and do some linear approximations. This linear approximation is similar to what you may have seen in a Calculus 1 course for a function of one variable. But here we could look at functions of 2 variables, 3 variables, or more. In this particular video, we will concern ourselves only with functions of 2 variables, but what we say does generalize to more variables, multidimensional spaces. So let's look at the definition of a directional derivative. Let's suppose that u is a unit vector in two-dimensional space R2, and being a unit vector means that the length of that vector is 1. This is the kind of notation that we use for the length of a vector. The length of u hat is 1. Often I will use a hat over a unit vector to remind us that it has length 1. And let's let f be a function of 2 variables. We can think of it as being the variables x and y to start with. And the directional derivative in the direction u hat at that point P, at a point P in R2, is given by this sort of formula. The derivative of f in the direction u hat at the point P is equal to the limit as delta t goes to 0 of f of p plus delta t times u hat minus f of p over delta t. When we look at this formula, we can see that we're multiplying the vector u hat by a scalar, delta t. And we know how to multiply a scalar times a vector. Here, p looks like it's a point in two-dimensional space in the xy plane, but we can think of p as being a vector too. A vector going from the origin to the point P that has some coordinates. So we can more or less vectorize this point by looking at a position vector related to P. So f of p plus delta t times u hat minus f of p over delta t. And like you do in the Calc 1 course, take the limit of this difference quotient as delta t goes to 0. The directional derivative of f in the direction u at the point P is the instantaneous rate of change of f starting at the point P in the direction of the vector u hat. So here's a picture with x and y axes. Here's a point, let's say its coordinates for instance could be 1, 2. And u hat is a unit vector which specifies this direction. So if you want to know how f changes starting at P and going in this direction specified by u hat, this directional derivative will give you that instantaneous rate of change. So it's similar to what you saw in Calc 1, except here, instead of going along, let's say, the x-axis, and looking at the instantaneous rate of change of a function, we are going in a different direction, perhaps in a different direction, specified by u, and the function f is a function of two variables in this case, those represented by points in the xy plane. So for example, if we let I be the vector going in the positive x direction, then that directional derivative in the direction I will just be the partial derivative of f with respect to x. If we let j be a unit vector in the positive y direction, then the directional derivative of f in that direction j will be the partial of our function f with respect to y. So, how can we compute that directional derivative for a particular unit vector u, a function f of, let's say, x and y, and a point P in the plane? At this stage, the only way that we have to compute it is by the definition involving a limit. So for our reference, here is the formula for that directional derivative of f in the direction u. So we're going to consider this problem. We're going to let the function f of xy be x squared plus y squared. We'll let u be this particular unit vector. Each of the components is 1 over the square root of 2. So this unit vector could be written, if we wanted to, as 1 over the square root of 2 times I plus j. And let P be the point in the plane 1, 2, the point at which we find that directional derivative. So we want to calculate this directional derivative. So starting at the point 1, 2, what we're doing basically is finding the instantaneous rate of change of f in that direction, square root of 1 over the square root of 2, 1 over the square root of 2. And here's a picture showing us the situation. Horizontal x-axis, vertical y-axis. Here's the point P, which has rectangular coordinates 1, 2. And here's a unit vector starting at P, which has components 1 over the square root of 2, 1 over the square root of 2. Let's remember that the directional derivative of f at P in the direction u is given by this formula. And let's look at this example. Let's let f of xy equal x squared plus y squared, and let u hat be the unit vector 1 over the square root of 2, 1 over the square root of 2. Let's calculate the directional derivative of f in the direction u, evaluated at a point P in the plane. So we're looking at this particular directional derivative, substituting in this for u and this for P. So, looking at this, by our definition, this is going to be the limit as delta t goes to 0, f of the point 1, 2, written as a vector in this case, a position vector, plus delta t times the unit vector, scalar times the vector here, minus f of 1, 2 divided by delta t. So if we add this vector and this vector, two-dimensional vectors together, it is equal to this vector here. And so we're taking the limit as delta t goes to 0 of this minus this divided by delta t. So let's see what happens. F of xy is x squared plus y squared. So f of this stuff is this first thing squared plus this second thing squared. F of 1, 2 is just 1 square plus 2 square, and it's divided by delta t. So we get this. If we expand these two squares of binomials, this stuff right here becomes this stuff right here. And then we're subtracting from that 1 plus 4 and dividing by delta t. If we look at this, we have a 1 plus 4 inside this brace, and we also subtract 1 plus 4. So that stuff adds or subtracts up to 0, and so this numerator becomes this. It's just missing the 1 and the 4 here, the 1 and the 4 there too. So we have all this stuff divided by delta t. If we look at this though, we have terms here, 1 term, 2 terms, 3 terms, 4 terms, all of which have at least a factor of delta t in them, and we're dividing by delta t. So subtract each of these terms by delta t, we can simplify this limit to this stuff right here. And then look at the limit of this as delta t goes to 0. 1/2 delta t will go to 0. This 1/2 delta t will go to 0. So the only thing left is, that's non-zero, is this term plus this term. And so we add those two together and we get 6 over the square root of 2. So that tells us then that the directional derivative of f in the direction given by this vector right here, evaluated at the point P, which is 1, 2, is 6 over the square root of 2, and this can be simplified a little bit. Multiply both numerator and denominator by the square root of 2, and it simplifies to 3 square root of 2. So going from here to here was just rationalizing the denominator. And now we're going to consider the linear approximation of f of p plus delta t times the unit vector in some direction. P is a point in the plane, delta t is small, and so we're going to approximate f of this point, assuming that we know already the value of f of p. So we're going to try to estimate f of p plus a little bit more in terms of the value of f of p. In Calculus 1, we saw a formula. F of x plus delta x is approximately equal to f of x plus f prime of x times delta x. We had this term, which basically you could consider a correction term to calculating f when you change the x value by just a small bit. In multivariable calculus, we will see very quickly, very shortly, that we have a similar formula. F of p plus delta t times our unit direction vector is approximately f of p plus delta t times the directional derivative in the direction u of f evaluated at p. So let's consider the following example problem. Still using the same function as before, still using the same unit vector u hat. So let's let f of xy be this, let u hat be this vector, which we saw we could write this way if we wanted to. We saw that the directional derivative of f in that direction u hat was 6 over the square root of 2. The directional derivative of f evaluated at the point 1, 2. So we notice that f of 1, 2 is 1 squared plus 2 squared, which is 5. And our problem is to use a linear approximation to estimate the value of f of 1.03, 2.03. So here's how our solution will go. We know that the derivative of f in the direction u at p is equal to this limit. If delta t is very small, we can get rid of this limit here and just say that this stuff is approximately equal to this fraction over here, and then multiply both sides by delta t. So if we do that and then arrange terms just slightly, we get that f of p plus delta t times u hat is approximately equal to f of p plus delta t times this directional derivative. Now, we're going to estimate f of 1.03, 2.03. So we want the t times delta t times u hat to be 0.03, 0.03. Can we do it for this particular u hat? Well, u hat is this vector right here. So delta t times this vector has to equal this vector. And that gives us for the first component, delta t times 1 to the square root of 2 is 0.03. Secondly, it has to satisfy delta t times 1 to the square root of 2 equals 0.03. Same equation. So in this particular case, for this particular direction, we can solve this. Delta t times this equals 0.03. Multiply both sides by the square root of 2, and we get delta t is 0.03 times square root of 2. So then we plug in all of those things into our approximation formula, which is right up here. So f of 1, 2 plus this stuff, which is 0.03, 0.03, that vector, is equal to f of, approximately equal to f of 1, 2 plus the delta t is this stuff right here times the directional derivative, which is this stuff right here. And we have square root of 2 over square root of 2, which is nice here. So this simplifies to 5 plus 0.03 times 6, which is 5.18. So what we have shown is our linear approximation to f of this is 5.18. Let's check our work by doing the same calculation on a calculator. F of 1.03, 2.03 is just 1.03 squared plus 2.03 squared. Punch all this into a scientific calculator, and you'll find that it's equal to 5.1818, very close to our linear approximation. Our linear approximation was pretty good because delta t was pretty small. So, in summary, what were we able to accomplish in this video? Well, we saw that the directional derivative of f in the direction u at the point P was given by this limit, and it looks quite a bit like the definition of the limit of a one-variable function, except in this case we have points with two components and vectors with coordinates, that is, and vectors with two components, but the formula looks very much like a Calc 1 formula. We saw that this represents the instantaneous rate of change of f in the direction u. We saw how to use this definition, this limit definition up here, to compute a directional derivative. We saw that the computation was easy in this case, but required a little bit of algebra, vector operations along the way. It took about one slide to do that calculation. We used that directional derivative to approximate the value of f at a slightly different point other than P, a point close to P, but in the direction of u hat. And that's what we did. In later videos, we will see how we can use the gradient, whatever that is, to calculate the directional derivative. And also, how can we use all of this stuff that we learned to calculate derivatives in other coordinate systems? For instance, what happens if we are looking at functions of polar variables, r and theta, polar coordinates, or cylindrical coordinates, or spherical coordinates? And why would we want to do that sort of thing? So that's where we're headed. So please stay tuned and we'll see what happens.